we'll jump right into it before we lead us into lunch with. We'll finish the section and start one more, and we'll get to lunch here, but an hour here, so bear with me as we get hungry into the afternoon. So far we talked about just kind of where we are right now in the modeling and study world. We talked a lot about model types, the generic, user-defined, manufacturer-specific kind of discussion. We'll probably pivot away from that almost entirely for the rest of the week. But I just want to make sure that we're all aware that it's still a consideration in the EMT world. Just the predisposition, again, is for most folks to think of EMT as being the real detailed, highly accurate simulation domain, right? So the predisposition, again, is also always that, or not always, but very often in the UD or in the EMT world that we're expecting kind of a real code, highly accurate model. But you may also see generic models, standardized models in the EMT space, right? And for the reasons we talked about before. Maybe it's far away, maybe you're just doing a research thing, maybe you're just testing something. Maybe that's all there is for that piece of equipment. So just keep that in mind as we go forward. Probably won't mention much of those two words, standard library or UDM again, but just keep it in mind as we go forward. So very important when we talk about EMT is that they're, from doing these types of things and going around and talking to people, you get the sense that when anyone says EMT, everyone already assumes it's a perfect model, right? You got an EMT model, it's exactly right. It's exactly what I need. It's a perfect representation of the product. That's what I've been given. That's where I'm starting from. That's not the case almost ever, especially for a lot of us who are doing work in the industry with the EMT models. And the key thing here is that if a model is not constructed right, that's from the manufacturer onwards. So the manufacturer piece, hopefully they're doing the validation piece and you're getting a better starting point. But when you take it over, you being the person doing the study work or helping people do the study work, now it's in your hands. You're the one controlling the data. And if you put together the model wrong, if you parameterize the model wrong, it's wrong, right? The perfect model, perfect code, if it got the wrong parameters, you connected it incorrectly, or you put the wrong things in the wrong place, it's wrong, right? And that goes for generics and library, whatever. Very important to keep in mind that to make changes, it should be thoughtful, to put them together, really to be thorough at the beginning of the process and keep that going forward to make sure that even if it's an EMT model, you give it the scrutiny it deserves, because everything, our job is to make sure we're being sure of the things we're studying. So again, EMT is not inherently accurate, but also when we talk about both domains, the phasor domain, positive phasor domain, they're not insufficient just because they're in a different domain, right? We all can agree, right, that in the EMT domain, if we're solving in the time series, we get a better waveform and it's a little more accurate, smaller time steps and things like that. But that doesn't mean there's no reason to do anything phasor domain positive sequence anymore. So there's a huge overlap between there's a significant overlap between what you can do in the best phasor domain model and what can be done in a not so great EMT model, right? So there's a big gap. And I was talking during the break, and this is important to keep in mind because we're probably not close to doing EMT everything by virtue of knowledge in the industry, by virtue of the models available, computational things we'll talk about. We're probably not going to have a full system EMT model. There are some really good examples of small systems who have had the luxury of the very significant need, like Hawaii has a full system EMT model, but they needed it, and it's a small system, so they can run it. You're not going to run the Eastern Interconnection in the EMT right now. Maybe Lucas can with his supercomputer at the office, but probably not. It's just a consideration we need to do there, and we also want to make sure as we go through processes and things like that we're not just jumping right to EMT as the new best thing and missing our current tools, but just let's learn about EMT, the benefits of EMT. Keep in mind that there's an overlap. And if we could all get agreement on EMT as the new shiny topical thing, maybe we could put some of those principles back into the phasor domain process and raise the bar for everything. So enhancements to both modeling requirements really helps get us these models and understanding that we need to make sure the grid transformation is reliable. So closing reliability gaps, we need both tools to do it, but we're going to focus on EMT for most of this. So, and the reason for that is, if you look at the Odessa 2, 2022, you'll see that with the exception of feeder under frequency disconnections or reductions, pretty much every one of those reductions can be studied in EMT. And when I say can be studied in EMT, I mean just like possible in the domain as far as solving and seeing the waveforms. The feeder under frequency no might be changing. The main impetus for the no that we published was that at the time of publishing, which was 2023 or 2024, there weren't any good ones, right? There weren't sufficient quality actual like relay EMT models there. So there's a no in both there for now. I have seen, I think Lucas, you've probably seen as well, there are some of the major relay manufacturers who are putting together EMT models. I don't know if they're very close, but it's been recognized as a problem. So we'll keep that out of the discussion. But besides that, everything we saw in the Odessa can be studied in EMT. So why don't we just do EMT for everything? Would be the easy next step, right? If we have one simulation domain that can study all these problems and capture them, if we do the accuracy right, the front end, why don't we just do it for everything? Well, a lot of different reasons, but the current paradigm is, huge, right? We talk about inertia momentum in the system. We also, as humans, have inertia and momentum. We're really like to, especially as engineers, like to do the same thing we've been doing. If it's not broken, why should we fix it? Is some of our mentalities, right? So there's a paradigm right now that we're stuck in, and it leaves gaps. We saw the gaps. We saw them with the unexpected reductions, the near 20,000 megawatts of disturbance reports, plus all the ones that aren't reported. And if you can do it, why not do it? Well, it's important to keep in mind that when we talk about grid reliability, we're talking about more than just ride-through events. So ride-through it's easy to fall into the mindset of just categorizing all big events as a failure to ride through an event to come offline, to cause cascading failure. That's the end of it. That's the bad ending of a reliability story. But it's not the only thing. Disturbance reports only tell the last chapter of this story. A big piece of grid reliability is normal operations, right? So that's primary frequency response, regular voltage slope response, power factor control, which we probably shouldn't use in the US, but it is used. Reactive power control, active power set points for ramping up and down for balancing, things like that. There is a whole bunch of reliability aspects that we need to, controls in a facility that need to be tuned to make sure that they're reliable. And a lot of these don't really need an EMT model. For a 2% voltage step change at your point of interconnection, the difference between an EMT model, full code EMT model, and a good phasor domain model is probably really small. For those small disturbances, you get a really good representation of the phasor domain because they're not extreme cases. The solution engine in the PSPD tool is perfectly capable of doing a small step like that. You may see some artifacts depending on whatever you're studying, but generally you're good there. That's also true with generic models as well. For a small voltage step change, if I have a test, I can curve fit a generic model to work for that small voltage test or that small voltage disturbance or small frequency disturbance. So that's why when we said earlier, that there is, as you get farther away from your study area, it's okay, right? Because for generic models, because of Mod 26 and Mod 27 from the NERC side, you're curve fitting those small events. So if I'm studying an area and I know that the surrounding area, they'll never see a disturbance larger than 1% voltage, I can represent that in a generic model. That's fine. I'm also going to miss these other things, but just to keep in mind that when we go through reliability studies and reasoning for studies, it's not always right through, but there's other things to keep in mind. And there's reasons to use different domains for different purposes. And as engineers, if we have multiple tools, it's best to use the right tool for the right job. Just in general, for either getting the right result or not over-engineering like we all like to do most of the time. So the other piece and why EMT can be a really good technical solution is that normal and abnormal operations, so like normal operations and ride-through, there's a lot of controller handoff between those two things. So a lot of more communications that you should be modeling, communication delays, sampling times, all that kind of stuff for the handoff and recovery. Really good for EMT. Fault ride-through in general is good to have done the EMT for these detailed event or detailed causes of reduction. But for simple stuff like PRT29, voltage and frequency tripping, PSPD is probably okay, right? So that's just to say with examples, there's while EMT simulations can be or are required to mitigate some of these risks, like the table in the back, you can't see some of these in the phasor domain. Keep in mind what you're studying, why you're studying it, and how the good is working, right? There's more than just ride through. So some other reliability needs I'll fly through here, especially for those who were in Florida because you saw these before. But big piece, maintaining system and voltage and frequency. That's to help power quality stay good for equipment. Helps keep the system values at nominal. Keeping them at nominal throughout normal operations means that when something bad happens, you have more margin, right? It's in quotes, but like you have more stability margin. Like if there's a fault event, you need a bunch of reactive power to keep the voltage up. If your controller is set up wrong and you're kind of railed out on the capacitive end, you don't have any more capability during the fault. So keeping things in normal operations, making sure you're testing and tuning the controls in normal operations to make sure you're not saturating and staying normal with margin, extremely important for voltage system or system voltage and for frequency for balancing. And these are also some things that, depending on what you're studying and how you're studying it, can be done in either. So active power controls is generally what do we see from active power controls? We have active power set point changes. So that's you give a set point change to a controller. In a detailed code-based phasor domain model and an EMT model, you probably get the same answer. In a standard library model, you may not get the right answer because of different ramp rates and different multiple ramp rates and things like that. And the two primary frequency responses, right? So primary frequency response we're all familiar with. Regular frequency response, you get outside your deadband, you operate in a droop, your active power changes to get to where you need to go. And the fast frequency response, which is often significantly more complex, happens on a much smaller time frame, and usually has complex manufacturer-specific controls. So for this example, for primary frequency response, PSPD, phasor domain, and EMT, they're going to be pretty similar. For fast frequency response, you might see some divergence there. For reactive power controls, so again, really high level reactive power set point, high quality PSPD, and EMT, pretty similar, same for power factors and limits, and for automatic voltage regulation. For general, simple, one slope, one deadband voltage regulation, there's probably not much difference for small disturbances between a standard library, a user-defined PSPD, and an EMT. If you start getting into like advanced AVR, so more than one slope, more than one gain, gains that may adjust themselves based on perceived system strength, cool, advanced stuff like that. You're not going to get those in a standard library model. You probably won't get them in a lot of even high quality PSPD models, and you're probably going to want to study that type of thing in the EMT model with the full code and the full parameters. Ride through is, I guess the bottom bullet says it all. Ride through is when everything starts diverging, right? You may have, even between two PSPD models, you may have a generic model and a PSPD user-defined model that look identical for a 1% voltage change, but as soon as you run any fault, they diverge by 30%. So that's major differences between just the implementation of the code, because ride-through controls, the main purpose of ride-through, we probably think the purpose of ride-through is to stay on the grid, to ride through disturbances. The main purpose of ride-through is to protect my equipment. The reason why protection settings exist is to take it offline before I burn my pieces of equipment up. So these are operating, ride-through controls are operating in extreme conditions. Each piece of equipment is different, capabilities are different, gains are different, the number of gains are different, thresholds are different. All of this means you really need detailed code, actual software code. Like we talked about, a lot of time that's already in the EMT by virtue. But again, you can have that type of floor get raised with the PSPD for these things. So the big things for ride through, you're at the extremes, really fast, really large fluctuations of frequency, voltage, whatever. You have that handoff between the inverters and the plant controllers, which can get complex depending on how many different things you have controlling the plant and whatever communication is set up. And the big thing, and really the EMT specific thing, because even the best PSPD models don't have all of them, is sampling times. So how long does the equipment actually take to read a sample? Is it every 40 milliseconds, every 20 milliseconds? No one's really doing continuous sampling of system quantities. Communication delays and protocols. You're not really modeling communication delays in the PSPD. I don't know if anyone really does that. I don't think I ever have done it. But again, that's in the EMT world. So how long does it take round trip for a signal to pass through the plant controller? There's a lot of misconception about that in the industry, right? I think even at AAA 2000, which I have a leadership role on, I think we said we recommended something implicitly about 200 milliseconds. I think 250, 200, 250. That's wildly fast. And even in ERCOT, right? If you look at ERCOT's model quality tests, procedures, you say that they may say you have to have your response completed in a second, full response, or 90% of your response in a second. And I think they use the words immediately for the beginning of the response. But what's immediate mean? Is immediate 200 milliseconds? Is immediate 500 milliseconds, a half a second? And a half a second is not out of the realm of possibility, especially if you have a plant controller, an RTAC for switching capacitors to other devices. You might have two plant controllers who need to talk to each other. And then if you actually go the real academic way, then it's all the error, right? Because then it could be, maybe I sampled that 1 millisecond of a 40 millisecond window, and now up to a second. Just communication time. And this is all stuff that gets missed almost entirely in the PSPD world, but can be modeled and often is modeled in the EMT world. But those are the main differences and main considerations for when we want to do a detail to really figure out what's going on in EMT study, is these types of limits in performance changes and communications. So key takeaways, I'm going to skip it because I'm behind. Did I say all this already? Yeah, we need to change the paradigm. We can really improve current practices right now in parallel with making better EMT practices, please. We don't have to ignore PSPD for now to make EMT work. We can use PSPD improvements as an on-ramp to EMT. If you want something a little easier for your team or for your own learning, if you get into the detailed modeling of PSPD, the jump to EMT is a lot easier. If you go from no modeling experience at all or bad modeling practices and engineering judgment and go right to EMT, you're not getting the benefit of EMT. You're just kind of doing the wrong thing in a different way. So we need to really kind of raise the floor for everybody in the industry here. Oh yeah, big one. They're not going away. PSPD is not going away. Phasor domain, PSSC, TSAT, power factor studies are not going to stop. They are the bread and butter of planning for a lot of good reasons. We'll talk about that in the kind of limitations piece of the presentation today. But high level computational burden, we don't have as many processors as we need to run a full system. They might not have EMT models available for a bunch of reasons we'll talk about. And not every study needs an EMT. You don't need to do EMT everything. And that's me giving an EMT course who loves EMT. You don't have to do EMT everything. But it's really important for specialized stuff, subsequent stuff. The special studies we're going to cover on end of Tuesday and Wednesday. Those are the main use cases where the EMT really shines above the benefit, or shows the benefit. And over-engineering is a real big concern here. If we see EMT as a cool software with all this level of detail, the first thing I do as an engineer is use every detail possible. Where you may not need to use every detail possible, but now you have this like playground of new unseen detail that I can mess around in. But keep that in mind. It's just because you can do something in EMT doesn't mean you should do something in EMT. Knowing what you're doing and why is important, and just mitigating the reliability issues right now needs use of both model domains or simulation domains, and the engineering judgment is extremely important. So slightly back on track, but still behind. So we're going to start with into the actual EMT simulations and introduction here. So previous section was just context, modeling, study paradigm. We're going to jump into EMT tools. I'm going to put this slide up here again, just for my remembering. Again, we're going to use EMT as a word for everything. So I'm going to not spend too much time on the basics, partially because I don't care as far as practical training, right? We're learning about a hammer, how to use the hammer. We don't need to know how the hammer was forged and how it's different from other hammers. We just want to use the hammer, our tool here. So just really basic, and Lucas maybe can jump in and be less basic because this is really high level, but the big difference between PSPD and EMT is that for the PSPD, you're basing it on phasor calculations. So it's like a simplification over a cycle, simplified average time calculations, but that gives you a very quick simulation time, and it gives you pretty good insight into things like power flow, voltages, and currents, right? Which is the main quantities we all kind of work with, but it assumes a quasi-steady state and sinusoidal balance, right? Which means you're missing things like unbalanced faults, really, really fast controller behavior, resonances, and things like that. And the reason why you get those things in the EMT world is that they're solving the differential equations each step. So it's in the time domain. You're actually resolving the entire waveform at whatever tiny time constant you're using. And Lucas is going to add probably better content.
Great, Alex. Yeah, so exactly what Alex is saying, right? So in PSPD, we are, the whole network is broken down into phasors, right? So imagine you have a series compensated transmission line. From the PSPD perspective, that basically gets collapsed into just an inductor that is smaller because of the series capacitance, right? Whereas we know from our circuit fundamentals that we have a series resonance on that transmission line. So that's a major problem for the network representation of PSPD, and we can say similar, in terms of all, system harmonics are basically not represented, the system resonances, and then it's a real problem. And yeah, the phase representation in PSPD, we just have an RMS number that represents the voltage of the system, whereas in EMT we actually have like the individual waveforms of all three phases. We can apply faults on individual phases, right? So this is one question we always get in courses where like, wait, you just applied a single underground fault. Didn't you have to do like a big calculation to figure out like the correct fault impedance to get the voltage drop to a certain amount? No, that's not a thing in EMT. You just apply the fault on a single phase and the voltage goes to zero because you actually have the three-phase voltage waveforms to play with. And yeah, in EMT, we can, the simulation time step is also much more flexible, I would say, than in PSCP. So we have the ability to study like extremely fast phenomena if we want to. So we can go down to like the nanosecond time scale and study very quick transients. You're really only limited by the size of the time step in terms of what type of phenomena you want to study in EMT. So that's, in special studies we'll talk about, hopefully we'll get there to talk about classical studies a little bit, and what those look like. So yeah, and then that has all kinds of implications on the IVR controls, right? In terms of how they react to unbalanced faults in the system. When we're doing these sort of model quality testing or design evaluations, a lot of the time the worst cases are unbalanced faults, where you are applying like a 2-Landgraf fault or something like that, and that causes a resultant overvoltage on the healthy phase and things like that. And all these things are missed in PSCP. So yeah, but anyways, back to you, Alex.
Thank you. Yeah, and I would keep in mind or point your attention to the little picture here, and I guess it's from AMO, so it's backwards because they're from Australia. you would think the time would go from left to right, but the time is going up from right to left here. And you'll see the kind of the windows here. So to Lucas's point about time step and studying the phenomenon, there's a lot of flexibility there. So the really small time step things on the right, so really fast converter controls and things like that, EMT can study its whole breadth. Where if we're talking about RMS type models or PSPD type models, the window of what you can study is much smaller and also much less discrete as far as the time step. So we'll keep that in mind for why that's important. So just generally, so that was kind of the math behind it, but just generally, and this is really high level and probably not all the way right, but we can talk about it if anyone has questions. But just generally, we've talked about them both together. The PSPD, much shorter simulation times. For EMT, much longer EMT or simulation times. And the example I like to use is we're doing a study with a regular laptop, like 4 or 8 core laptop, so I guess a good laptop. And we were running a partially equivalent IBR plan, so like 11 machines, one wind farm equivalized to 11 machines, and a 30-second run to about 28 hours. Right, so we're talking a significantly different time scale of study time and computational burden. You're doing that same thing, a fully disaggregated, full 100 machine, even dynamic PSPD in, a 30-second run in 6 seconds, right? 10 seconds. So 10 seconds or almost a day and a half. Very different computational burden. So it's very important to make sure we're getting the most out of it. So part of the reason is the level of detail and accuracy is very different. There's a star there because those are generalizations. There are some manufacturers or model builders who build really bad EMT models. They're not accurate. But generally speaking, you get more detail and accuracy in the EMT and less detail and accuracy in the PSPD. I'm saying here, right, the PSPD is kind of the sledgehammer, the everyday tool. We're using it to hammer the study process into submission because we have too much work to do. It's our kind of everyday tool. We're using it for every task. We've got to break a rock, sledgehammer, break something else, sledgehammer. EMT is a scalpel in this kind of metaphor, right? When doing an EMT study, you're solving a specific problem. There's a ride-through problem. There's a transformer saturation issue. There's an SSO, SSR. The grid is super weak. It's a really specific thing to test and tune for, or test and study, really direct, precise tool to study those things. PSPD, we've talked about it, a lot more prevalence of generic standard libraries, and EMTs most often manufacturer specific. Talked about the mapping, a lot easier to EMT versus PSPD. System strength is a big one. We talk about screening and a little bit of, we have a session on weak grid studies. But as we transform, the grid's getting weaker, just in general, weaker in quotes, depending how you want to define that. And as the system gets weaker and the system strength is lower, you really hit the edges of what PSPD can do, like physically can do in the simulation domain. My number, which I use, which is not what everyone else uses, so this is my opinion, right, is like SCR 5 or below is about where you start seeing, again, for lack of a better term, weird stuff happen in the PSPD world. And that's not to say it's always wrong. It just might be strange. And it might not be controller related. It might not be code related. It's just the simulation engine is not great at that level of system strength because of the way it works and the calculations it's using. So as the system gets weaker and we do more radial interconnections, there's probably a lot of us who have and continue to do studies at an SCR of 1.5 in PSSE with a generic model, and those are the three things you should never do together. But it's just what we do. It's how the paradigm is set up. So very important that when we at low system strength special cases, areas with harmonics or serious compensated lines, things like that, low system strength, EMT is the tool to solve the special case studies that we talk about tomorrow and Wednesday in a lot of detail. So just to kind of reshape us here on some of the needs, we're gonna start with the needs of EMT. Again, the main need is the system's strength is reducing. Just in general, really boiled down to one thing, is the system strength is reducing significantly. Every grid following IBR we connect, again, super general, will reduce the system strength in one way or another. And what that means is we can't have the same assumptions anymore. Everything, same assumptions across the board. We have to change all of our assumptions with the system strength is reducing. That's because with a lower system strength, any perturbation is going to be larger and happen faster. So if you heard of rate of change of frequency or Rokov, lower system strength, higher Rokov. So you get a much steeper, much faster change in frequency for the same stimulus, which is something we really need to plan for, both in the under frequency load shedding world or planning world, but also higher rate of change of frequency means more stress on the simulation domain. One of the main failures of PSPD is that if frequency moves really quickly or a voltage moves really quickly, you get instantaneous calculation errors and things like that in the simulation engine. So in general, like the faster and more extreme you move, the harder it is for the simulation to actually keep up. Again, and also system voltage is going to be less firm. Those are my words to explain it, which means that basically if you're in a lower system strength, for every kind of change or MVAR you put in of reactive power to the system, the voltage will change more, right? There's less resistance to what you're doing, which means that errors in controller tuning will have a bigger effect, right? 1 megabar in a strong system of error, much less of a disturbance than 1 megabar in a really weak system, just for example. So, so the EMT simulations are really, really paramount for representing complex resources on a weakening system. I have PSPD in here as well, because we're also in a world where maybe one interconnection of an IVR for 3 contingencies is an SCR of 1, but for the rest of them, it's 10, right? So you need to study all 150, that's probably way too small a number. You need to study all of your interconnection study contingencies or all of your planning contingencies in the EMT, because a couple of them are low, probably not. So again, keep in mind what you're studying and how you're studying it and using the tools that you should be using. So keeping in mind that kind of the bigger piece of this, the kind of time frame that the EMT covers, that's great for us because as system strength is weakening, the time frame shortening as well. So big differences between synchronous machines and IVRs. We talked about it. Synchronous machines, physical properties, large rotating mass, relatively slower things are occurring. It goes out the window with power electronics and software. You can do very, very fast things, very extreme things, very quickly, right? So what that means, based on the software-based controls and things like that, as we keep interconnecting more IVRs into the system, we're shifting that window of time frame to the left, right? So as we put more and more fast controls on the system, as we're taking off slower controls, the average window is shifting to the shorter time frame. So it's going to continue to happen. And to study those things in that electromagnetic window, electromechanical window, EMT is a really good tool for that. So we're getting to a point where not fast, but it's in proportion to the transition to where we're going to need to keep up with these types of fast controls. So with more IVRs in the system, also those controls become really, faster controls become really important just for mitigating major swings and things like that. Fast transients and responses to those transients are going to play a really big role because the system's weaker and you're all kind of fighting each other, and tuning and testing is really important. Communications in the plant and outside the plant, really important as well. But in general, the system response is becoming faster. So why is that happening? System strength. This is a little bit of, I'm not going to go too deep into system strength. We did a lot of system strength talk in the interconnection class we did a couple weeks ago, so I'll save those folks who did both. And if you want to, you can go listen to those slides because there's a lot more discussion on system strength. But just for us here, I've already said it a bunch of times, but we're moving from big spinning masses to software-based low fault current type of thing. So a big piece of this, and we'll do a little sidebar into protection, is it's very clear that with fewer synchronous machines, we have a lot less fault current on the system. So blue here is a synchronous machine's fault current. A red is just how we used to tell inverters to operate, which is get offline and don't bother me anymore, which is not a paradigm we were in any longer. But the green is an IVR with ride-through, right? So you'll see the massive magnitude here between the two different things. So this is something where, and the reason why I have it in here is something where highly detailed, high quality EMT protection studies can help us out. A really specific use case, we do need actual EMT relay models with real code. because the entire system protection paradigm is basically rooted in fault current. Big generalization, but a lot of protection engineers, system protection, we're depending on the paradigm of having a lot of fault current available. With a lot less fault current available, we're opening ourselves up to missed operations and things like that. And maybe we don't trip on that anymore. Maybe we choose a different quantity to trip on. Maybe we're not tripping on negative sequence quantities. Maybe we, there are other phenomenon that happen when an IBR goes through right through, or there's a fault or disturbance that happens in an IBR dominated grid. There are other things to trip offline or to stop tripping offline for. So doing that type of detailed work in this time domain in an EMT type model could kind of help us stop admiring the problem of system protection that we've been doing for a long time, and could be a way to get there. So this is a pitch for anyone who has the ability to do that and to get that going, would really, really be helpful for us here. So why is it, again, I guess we already said this, but why is it really important? You get about 6 times more fault current from a single machine. You're currently using fault current to trigger as a primary trigger. If you don't have that, we got to figure out something else. And it's hard to do that on the fly. Protection engineers don't. Any protection engineers in the room? Oh, you former, recovering protection engineer. They really are risk adverse in the best way. Like if you ever talk to, you ask a protection engineer to get you data from the field, you get it as found, as left, as expected. It's wild. It's fantastic, right? So that kind of thing is you don't want to test out a new protection scheme on the fly. You're not going to go change the transmission relays and kind of say like, oh, that made sense. Let's do it. Studying it in detail in the new like real responses of an IBR with the response of the system is extremely important. And the reason why that's an EMT specific thing is 1, probably lower system strength. 2, the IBRs do provide fault current. But the fault currents basically change with all the control changes. I can have the same inverter, 2 different fault right through gains. I have different fault current, right? So to understand actually how much fault current you're getting, you need a real detailed code model to show you how the gains are and how they're doing it. Because otherwise, you're not getting the real, the actual fault current. There's no one size fits all because of all the changes, difference in manufacturers, difference between 2 manufacturers in the same different parameterizations. So instead of trying to fit the system into the old protection paradigm, using EMT to kind of study and assess those things is extremely, extremely important. And it's not a use case I've seen quite yet. So if anyone wants to go back and tell their boss to do that, help you out with that, would be really helpful for the industry. So a little bit of example on system strength, super high level. We probably have all seen something similar. But if we consider the system as this drive shaft, and we have a bunch of signal generators connected to a chain, right? They're all spinning in the same direction. If I want to impede that drive shaft and kind of hold it, if there's a lot of other machines connected to there, I'm going to get a lot of resistance to that change, right? This is an active power and frequency kind of discussion, but similar principles hold for reactive power as well. So if I take one away, I do. All right, if I take one away, I had an extra slide in there. And I try to do the same impedance or same holding onto the drive shaft. There's less synchronous machines, there's less torque, less resistance, right? Really high level and simple there. So if I take more away, even less resistance, which again means that everything I do to disturb that drive shaft, I get a bigger change, which means really important to have specific controls because again, a wrong control in IBR could cause a big change. And a big change in a weak system is a huge change. And we don't really plan for huge changes like that. And it really underscores the importance of manufacturer-specific, site-specific models. So the main reliability gaps right now that we are kind of working towards or that are kind of EMT specific here, there are others, but first one, predispositions we all have for modeling. We talked about it a little bit. I'll briefly talk about it again, then we're done. Low system strength, systems getting weaker, especially in pockets with lots of IBRs. Very complex resources compared to the previous. The system is changing extremely quickly. And the model quality and accuracy, the roots of the study process need to be appropriate and true. And the mapping of models to the reality, right? None of the study work we do means anything unless we can actually put a solution in the ground. Otherwise, we're just doing studies for the sake of it. Just a saying from a guy at FERC that maybe we'll talk about on lunch. It's really funny about that. So these two big ones at the bottom here, we're going to talk about in a lot more detail in the model creation benchmarking session of this training. So I'll skip them for now, but we'll talk about the other ones. So again, I kind of touched on these a little bit, but the predispositions we have to break for EMT is they're not PSPD is not going away. They're not obsolete. They can be highly accurate, and they still do have good use cases. So there's a reason why I'm repeating it, and it's because we can't forget about it. It's still the mainstay of study work, but we still also need to kind of work forward from the EMT side. So EMT is not the only right tool for everything. If we look at the slide with the NERC stuff, for those specific things, EMT was a great tool. It would have captured all of them, but it's not a one-size-fits-all for everything. So just keep that in mind. It's not going to be a silver bullet for your entire issues, but it's a really good tool if used right for the right circumstances. The EMT model is not accurate just because it's an EMT model. Usability, parameterization, everything like that. And again, not everything needs an actual EMT simulation. So another big reliability gap that we're trying to fill here is system strength is weakening. I said about 3 to 5 for PSPD is where we start seeing big problems or weird problems or just frankly wrong results. And again, the scary thing about wrong results is wrong results could look really great. They're still wrong, right? I've seen a lot of models sent back to me at 3 in the morning because someone's mad at me. And they say, well, the model didn't match the process. And I said, look at the model quality test for MERCOT and it's perfect. And it's like, well, that was the perfect model. It didn't work in the system strength that you're doing it in. You ran the studies on ERCOT's model quality test, which is infinite grid. You never actually ran something at a low short circuit strength, so we can't be sure how it's going to perform down there. So really important, and kind of in line with that, we need advanced control features to keep the stability margin. We can't, 1 for cost, and 2 for time. We can't just build transmission for everything, even though it could be a good idea. It was what got us to where we are now. Like the reason we have stability margin right now is because there was a mindset where we just build transmission all the time. But to efficiently use what we have now, advanced control features are really important. But those don't usually exist in the PSPD models for a bunch of reasons we already talked about. And again, the mapping. Low system strength is one of those things where you almost always get site-specific tuning, a specific site-specific tuning with very bespoke parameters. I can't put it into the system, then the study looks great, but the real product for that contingency, the real plant is still going to do bad stuff in the field. We can't do that. The EMT, on the other hand, really good at studying low short circuit ratios. I put less than 3. Was there a low? There probably isn't a low, right? We haven't found it yet. So, there's just, below 3 is what was good for, or, a really good use case. They often contain all the relevant controls by virtue of the fact that most manufacturers throw all their information into the EMT model, and much better mapping and capability for putting those things into the real world from the simulation world. The complexity of resources, I touched on it a little bit. But the big one is, and this is, I don't know if it's like a North America specific thing, but we love third-party plant controllers in the US or North America for our facilities. A lot of times, you're not getting a third-party plant controller model, right? You're getting a third-party consultant or communications firm who's done a great work for actually making your facility like communicate in real world, but then they give you a generic FC model, right? Which obviously does not match all the detailed code and things they put together. Very big gap there with the complexity of resources. The other thing that happens a lot in the PSPD world is you may be using a plant controller that doesn't exist ever. Especially in the North American market, there are a few major manufacturers who, if you ask them for a PSPD model, you get a WEC generic model with a REPC and with just a plant controller in there as part of the package, but they don't sell them in the US. And you would never guess that. You would never know unless you actually saw the detail of the cut sheet. So the complexity can get kind of missed if we're living in the PSPD world as well. And then we all, again, the communication delays, communication protocols, all that other stuff. The ability of the EMT to actually put that stuff in the model, huge for actually studying these things. If I get an EMT model and I see a Rep C representation of a plant controller in there, my red flags are up, and I ask a lot of questions after that. If I go into an EMT and I see an actual user written model from a consultant who makes plant controllers, then I'm feeling better about it. And it also has the communication protocols and the time delays, all that stuff in there as well. So mitigating reliability needs is why we do studies. We study things and plan things so that if something comes up in the study, we can fix it. We talked about it again, so I'll just repeat it quickly. Really hard to represent the on-site tuning to start your study with, and to go backwards. And also the big thing is PSPD probably doesn't have advanced controls. So in situations where, for an active power set point change, if I'm getting an argument with ERCOT and they say you're not moving fast enough, like I asked you to, maybe the manufacturer product has 3 ramp rates and you need to tune some combination of 3 of them. The PSPD might only have 1. So how do you make a solution that works with both? It can be very difficult. And again, putting it actually into the field is the last most difficult piece as well. EMT makes it a lot easier by level of detail and by virtue of how those models are created and what they're used for. So these are really critical, especially for the efficient use and the reliability of the power system. That's just extremely important. So new grid issues, big EMT use case as well. So I'm using new in quotes because some of these aren't new, but they're more prevalent, which to some of us means they're new, including me for a lot of them. But you're not going to do a subsynchronous interaction study. You're not going to do imbalance faults. You're not going to do harmonic power quality analysis in EMT or in PSPD. You might not do the last one in EMT either, depending on what you're doing. But just generally, these things that we see popping all the time, oscillations, harmonics, distance to series compensated lines, PSPD is not the domain to study those things in. Very difficult to study interactions with controllers because a lot of control interaction is based on weird time step mismatches or advanced controls or communication handoffs and holds and samples and all those types of things that just don't exist in those models. So to study those things, EMT is a piece here. Having all those delays and actual control and handoffs and things like that, very important for actually seeing what's happening. And if you can't model what's happening, you can't fix it and you can't put it back. So the different use cases for EMT studies, this is for IVR specifically. I think we'll probably have some content on use cases for EMT with large loads and synchronous machines in a couple of days, but this is IVR specific right now. So like we talked about a lot of these, but the big ones as we get moving forward are very high IVR penetration. So we have areas in North America where we're getting to instantaneous penetrations of near 100. So we're there for some of these really detailed use cases in island networks. So Texas is an island network, Hawaii is an island network. That just kind of makes everything worse, if for lack of a better term. So those needs for the EMT domain are very important there. So SSCI, subsynchronous control interactions, unbalanced faults, power quality, controller interactions, all things we talked about. The detailed behavior and ride-through, very important. Good for use case for EMT. Protection system operation, like we talked about in the other slide. Studying those things in real detail, seeing how they're actually going to work and sample and do that type of thing. Short circuit current analysis, again, for IBRs, you need the detailed controls to know what you're getting out of it. There's no, and you can, because some areas ask for it, but like you're not mapping an IBR to like an X double prime D type cut sheet that you would submit for a fault current type of study. It just is not going to happen. I mean, it happens because you have to, but it shouldn't happen. But the use case is actually studying that. And the big one that we'll talk about a little bit at some point, probably after lunch, is benchmarking positive sequence models. So we'll talk about why EMT is good for that and why we should benchmark positive sequence models because they're extremely important here. So the benefits kind of hit it through kind of context throughout, but the benefits of the EMT, very robust solution engine. We're solving everything across the entire waveform. We're in the time domain. We know that domain, like mentally. You're really good at low system strength conditions. Another benefit in the EMT is at the level of detail, you can actually put mechanics in there, depending on how you build your models. So say you're a manufacturer who does type 3 wind, you can actually, in the EMT model, because of the detail and the differential equations, you can actually put blade wobble and stuff in there. So if you've ever seen a type 3 wind fault ride through in an EMT program, and you see the little, like, it's a profile, but it's wiggling, that's the blade mechanics probably. So it's really important to do. How much do you get out of it? It depends on what you're studying and why you're studying it. But it's a really important thing to represent. Very often have real code, highly mapped representations, very visual representations as well. You can kind of see where the devices are, the equipment is, you can click through the control diagrams and click through the control blocks and things like that. And then the new grid issues, SSCI, SSR, harmonics, weak grids, that kind of stuff. Very big benefit from the EMT. So again, to the question of earlier, why don't we just do EMT for everything? Big one, number one, probably in my mind, is just a very high computational burden. Physically, we go through that. Like, even if we had everyone who was doing power system studies an EMT expert, imagine if every interconnection study, every run took a day, 24 straight hours. That's a big computational burden. And I don't know how folks who work at the utilities are now, but it's very hard to get it. If I wanted a really fancy laptop, it's really hard to convince your boss you need a 12-core laptop. I did have some experience today, so we got like 600 cores, but not for dynamics, for something else. So very, very big limiter there is the actual computational burden. You can buy, like, off the shelf, what are they called, Lucas? The Threadripper.
Yeah, the Threadripper.
Yeah, you can buy a very fancy, very strong computer for this. But again, do you really need to run that type of thing? And who has access to that? And how do you convince your boss $50,000 for a computer is a good idea? Very big impediment. The other one is very steep learning curve, both the tools and the problems that you're trying to solve. And that kind of goes back to the discussion of knowing what you're studying and why you're studying them. For a PSPD, the software and the things you're studying are relatively more simple and kind of more close to what we all learned. I know what fault response should look like. I know that there's a frequency disturbance and the frequency is high, the power should go down, and vice versa. And if I want to keep the voltage on, I go, inductive. In the PSPD side, the simple things, they all make a lot of sense. So the problems that I'm trying to solve, I've already probably learned them. I'm just kind of getting a refresher throughout. And then the other side for the EMT world is that we're doing a bunch of other complex stuff. And it's a little bit less intuitive to understand how, near a series compensated line, my series subsynchronous issues are going to exacerbate. If I'm a really weak grid, what does that mean for control theory and detailed control theory? Because a lot of EMT work is you're in the weeds of the control parameters and blocks and code and things like that. So you're learning, there's a big learning curve for the actual problems you're solving and the tools, because the tools are much more complex in almost every way than a phasor domain program. The interfaces look the same or very similar, with a level of detail, level of complexity. Debugging a problem in EMT versus in a PSPD is wildly different and very, very hard. They're not hard to learn, but very different to learn, different mindset. The other limitation here, again, we've mentioned a bunch of times, is that the EMT models are only as good as they're parameterized to be, taking out of the context that they have to be right in the first place. Let's say we trust the OEMs to make a right model always, which might not be the case, but if they get it wrong, they'll fix it. So even if we trust the blocks being correct, wrong parameterization means wrong model. So this is the exact same limitation. One of the main limitations of the PSPD as well is we're just not using them right. Which, if you're not using it right, why would you in the study in the first place? So the big one, which is a lot less of an issue in the PSPD world, because especially for renewables or IBRs, by the time they were interconnecting in earnest, we were already somewhat mature for PSPD modeling in one way or the other. So A lot of IBRs out there have a PSPD model somewhere in the planning process. The developer might have one, even if it's like a random type 2 wind machine model from PSSE from 2012. You got it, right? You have something you have from some sort of the source of truth. EMT models might not exist, just in general, just literally may not exist. And there's two different types of not exist, right? There's, I bought a product from the manufacturer. They never built EMT models because it wasn't ever a thing in the last couple of years. They're out of business now. How do I get an EMT model? I don't have a manufacturer to go for. I don't even know really the inside of this equipment. I may probably have a PSPD model I can benchmark against, but that's it. Huge limitation, right? You've already kind of removed the usefulness of EMT at that point, right? You're already guessing about the whole parameterization, so you're kind of losing the use case of EMT. The other not exist is, and I'm using not exist in the way that developers and OEMs may use it, which means it's just hard to get it. So a lot of times you might hear, I don't have it. And then if you dig down, then the answer is maybe I have it. Or maybe I don't have it, but I know the equipment, I have old code, and I can get you an EMT model for $500,000 in 18 months. Is kind of the discussion you get there. So, and I don't know if I have content on this later, but it kind of feeds into the other one, the last one, which is the lack of regulatory clarity. And why retroactivity of requirements is extremely important discussion, especially for EMT, but just in general. So having retroactive EMT requirements makes sense if you go back a couple of years, right? If I say, if you interconnected before or after 2020, what did ERCOT use for the cutoff? Is it 2020? Whatever. Well, they used something that was reasonable. So let's say 2020, right? If you retroactive to 2020, if you interconnected afterwards, your manufacturer, we know your manufacturer built the EMT model, just go get it. That's one way. If you say every single inverter-based resource who's ever connected to my system has to produce me an EMT model in a year, that is that's a requirement that goes the opposite of what you're trying to do for reliability. Because there are some manufacturers, and something we dealt with on the NERC side when coming up with the modeling and write the requirements, is some of them might just disconnect. It's cheaper business decision for them to just get off the grid and do it again in a different project, different area, different requirements. So it can be a double-edged sword. The other piece is you may not get a good EMT requirement if 2/3 of the balloting body doesn't have the ability to get one. Right? They're going to vote no because they can't get one. So very important in the context of EMT and models and model provisions that retroactivity is top on mind. Just to be reasonable about it. Right? It's not just a parent asking where you hid something. It's, well, I didn't hide it, I just don't have it. Right? There are real issues, real pragmatic situations where it just physically doesn't exist. And the regulatory clarity is very important for that aspect too. There's a third doesn't exist for an EMT model. And the third low that doesn't exist is when I was interconnecting my facility, I didn't need one at the time. Right? So there's not every region in the US requires an EMT model to submit to interconnect your facility. So for those of you who don't or haven't lived in the world of developer and manufacturer negotiation, there's a big thing about service contracts and who has what responsibility afterwards, after you hit commercial operation. And almost nobody includes anything in there about models, which means if I interconnect to the system and I've hit COD and I'm into service contract land, and I didn't include an EMT model in there, well, now I don't get it for free. It's not in my contract. Right. So that's the third, I don't have it. And that's, again, where it becomes, a huge cost, or it could become a cost. So the regulatory clarity piece is also very important to get them, right? If you say, starting in 2025 in my area, every interconnecting IBR or plant in general has to have an EMT model, you're going to get one. Because the manufacturers are all going to see that and they're all going to give you one. If you don't do that, then it's kind of up to everyone to do their own best due diligence at the table there. Or if you don't, the opportunity cost for getting an EMT model is huge. So just in general for modeling specifically, especially for EMTs because of just their nature and how they're treated. Really important to use the leverage you have in the interconnection process, just in general, for everybody through requirements to get it. There's a piece of 2023 or 2023 that says only submit an EMT model if you're doing a study. Well, it might be useful for folks to take this kind of needs and benefits pieces of knowledge here, go tell someone who can make a requirement and say, hey, our system might have some of these things in the next 5 years. We probably should start asking for EMT models now as part of the interconnection process. Because it's much easier to have it on a shelf and use it and ask questions about it later. Even if you get a basic EMT model, it's a lot easier for me to go to the manufacturer and say, hey, I have this model, can you help me out with it? Than just say, hey, I need a model by tomorrow. I know we didn't buy it before, but we need it now. And that's a whole different conversation. So this was just a slide to say that a lot of benefits, you can do a lot of good with it, but there are some real, oh, this is really bad grammar, really limiting limitations, right? There are, when we talk about benefits, pros and cons, usually it's like, well, we can look past all the cons and we don't have to worry about them because the benefit outweighs it. This is really good benefit, but also really real world limitations that right now we don't really have good solutions for. So just to say again, even though it's a great tool, you've got to use tools with intention. And with that,